Okay, so today we are going to discuss CRDTs, conflictly replicated data types. So it is present, authors are Mark, Nuno, Carlos, and Marek. So yeah, let's go ahead. So yes, so mostly so introduction is that so there is comparison between strong consistency and eventual consistency, right? So in strong consistency, you can get total global orders, which can be easier to reason about, right? But there is a performance and scalability bottleneck because it requires consensus, and you have to make compromise between availability and consistency uh, from the cap theorem, right? And at the moment of partition, and also it only tolerates n/2 faults. So, and the pros of eventual consistency are, so it promises better availability and performance, so that you do not have to replicate all the writes to all the n/2 replicas. You can immediately write on the local replica, and so yeah, so mostly updates will happen without sync, right? So, and also it can tolerate n-1 fault. So if all the other replica besides you are connected to all goes down, you can still give your rights. So, but the problem with them is that concurrent updates may conflict, and you need to, after the network partition resolves, you have to roll back some updates, right? And also at the time when this paper was presented, most of the designs for the eventual consistency were more ad hoc, and they used to be error prone. So mostly, yes, so they have provided a formalization for this. So mostly this paper contributes a solution to cap problem, a compromise kind of, which they define as a strong eventual consistency. So when they formalize this strong eventual consistency and CRDTs, they provide the sufficient conditions for the SEC. Then the strong equivalence between those two conditions, and how SEC is incomparable to sequential consistency. Then they also provided basic examples of the CRDTs, and examples of the CRDTs mostly. Yeah. So so here the system model they consider for the CRDT is that there are Byzantine processes interconnected by asynchronous networks, and network can partition and recover. So mostly there are two types of objects they are considering: state-based objects and operation-based objects. So mostly let's start with state-based objects. So it's mostly, so for at every replica, it will update will modify the state of that single replica. Then every replica will send that local state to other replicas, and the replica, based on the new information, it will merge to new state into its own state. And mostly they are all the fully connected, or at least all the replicas are connected to each other. So eventually they will all receive the new updated information. So mostly here the state-based object, as a formalization, they are considered a tuple, which will have a payload set, initial set. So these are the operations that you can execute on that tuple, on that objects. So that is query object, update query function, update function, and merge function. So mostly queries are local, right? You ask them, they give them the it will return the value of that object, and then updates will write the local update, and merge will periodically send those um, updated state to the other replicas. So here how the causal history will look like. So suppose the causal history is the array of C0, C1, and right. So suppose here at the causal history will look like, so on query, history will look same. So here the CI is the causal history of I on kth execution, of ith replica on kth execution. So here on the query function, it will remain same, and on update function, there will be a union of the current causality history plus that update function with the parameter. Here A is the parameter passed to the update function, and on merge there will be a union of two causal histories of the other replica and your current replica. And so yeah, so that's mostly it. So mostly, let's digress to the partial order. So just this is most of a revision of what is a partial order. So mostly a partial order is a binary relation that has a is a set which has a binary relation between its objects, and which follows these conditions that every element is related to itself, and there every two distinct elements can only be uh, related to one way, not in the both direction. And also the third one is the transitive property. So if A less than B, B less than C, then A is less than C. So it's more of a composition or superset type. So and so semi-lattice is a abstraction that is created above using the partial order set. So semi-lattice is a partial order set which has a join operation which will give the least upper bound for those two sets on which we are doing the joint operation. So mostly it means is that if for all x and y there should exist a z where x and y are less than z, and also there should not exist a z dash where so yeah, so here is a mistake that here the middle one should be z as z dash, that x and y where they are less than z dash and also they are less than z. So there should not be any element between z and xy. So z should be the least upper bound. So and also the join operations should follow the associative properties. So that means that the order of join operation does not matter. I mean, you know, basically you can group them and group the join operation, and so it should not matter group wise, and also individually the community. So uh, x join y, y join x. Yeah, there is again a typo, and also it should be idempotent. So if you join x to x, then it should be x. So mostly here the example is that integer that are having a binary relation of less than equal to. So mostly their join can be a max of x comma y. So this will obviously satisfy all these properties. So it can satisfy idempotent, right? So x comma x will give you x. Then the max between three operation will also give you the same value regardless of the order you execute that. So mostly the requirement for to perform this state-based type of operations is that it should the payload should form a semi-lattice, and they are either updates are in increasing form, and the merge operation should compute the least upper bound. So if if these conditions are satisfied, then the replicas will converge to the least upper bound. So yes, mostly these are the necessary condition for state-based objects, and also it is idempotent. So if one replica sends the payload multiple times, then also it will not be a problem because the merge operation will be idempotent. So now they actually give the definition of strong eventual consistency. So the first three conditions are for um, eventual consistency. So eventual consistency should have eventual delivery, and that. if the updates are eventually delivered, and conversions that have delivered the same updates eventually reach the equivalent state, and termination that all methods should execute. So for strong eventual consistency, you need an extra condition called strong convergence. So that means which states that correct replicas that have delivered the same updates should have equivalent state. So this is the extra condition for this SEC. And so now let's move on to operation-based CRDTs. So our operation-based CRDT, the tuple is defined as payload set, initial set, then query function, then prepare update, effect update, and delivery precondition. So mostly here, as you can see, the update is broken down in two phases. So the first phase is at source. So there will be no side effect, and then if effect update will be that whenever the precondition got hit, it will send the updates to the other replicas. So and that will merge those updates to its own causal history. So here the causal history will, on query and prepare update, the causal history will remain same. Only on the effect update, the causal history will merge the current updates. So mostly for based objects, all the requirement is that all replicas should execute all operations in delivery order, where downstream precondition is true. So mostly they have to send the delivery updates in a sequence wise. So so for concurrent update, it can receive in any order. So some two replicas get same update at the same time. So that for that it can so third replica can receive those updates um, in any order. But if there is some happen before relationship between those updates, then they should be received on the other replicas in the causal order. And also as the concurrent operation should be commutative. So because they can be received at other replicas in any order. So here also, so basically there is a theorem which formalizes this, that assuming the causal delivery of updates and method termination, any based object that satisfies the commutative property for all concurrent updates and whose delivery precondition is satisfied by causal delivery is SEC, and thus it can work as an based object. So here you have to make sure that all your updates are only it needs an exactly once delivery uh, conditions, that all your updates to other replica should only be sent exactly once only. So that is the main drawback of the operation based CRDTs. So mostly, so these are the results from the all this formalization. So they have talked about fault tolerance and cap theorem, and how op-based CRDTs and state-based CRDTs are equivalent, and they give a proof for that strong eventual consistency is incomparable to sequential consistency. So let's talk about fault tolerance. So mostly CAP says that we have to choose between availability or consistency, right? So for most of the business, availability is top priority, right? So suppose Amazon shopping cart, they need to make sure that you can always add items to the shopping cart. So it's good for the business. So, but if you do that, then you have to compromise this consistency. I mean, so you do not have to give up all the consistency. Cap theorem only talks about the strong consistency, right? So you can um, uh, have strong eventual consistency. So which is always available for both read and write, regardless of the network condition. And also it provides extreme fault tolerance, right, for of n minus one replicas. because you do not need a consensus. So so now let's talk about the proof between that object-based replicas are similar to the state-based replicas. So here they do is this emulation of ob-based object using the state-based object. So suppose for the state-based object, right? Right. So this is the object tuple for the state-based object, and this is the object tuple for ob-based object. So here mostly the interface remains same, that query update remains same, and here the updates is broken down at the prepare update and effect update. So suppose that so mostly prepare update has the same interface as the update method in the um, state-based object, and also then the merge and the effect update remains, right? So they how they are similar. So mostly if you have seen previously that mostly merge is also commutative and effect updates are also commutative. So as a in terms of their principles of working, they will also remain same. So in a way you can easily emulate operation based object using the state based object. So here, yeah, mostly it says that monotonic seminata is almost equivalent to the commutative data types, commutative replicated data types. So what you can do is you can use start with state-based objects because they are easier to reason about, and then convert it to ob-based object because they are better in terms of efficiency. As the states grow larger and larger, it will be mm, difficult to send them, or it will require a large amount of bandwidth for this for sending all those states. So objects can have delta. You can only send the delta. You only need to send the delta of the operations. So here there is another proof that SEC is incomparable to sequential consistency. So mostly generally state-based replicas mostly executes a sequence of read, update, read, and merge, right? So in sequential, so in addition to the sequential behavior, CRDT adds a concurrent behavior, that ability to update and write in different replica at the same place at the same time. So so that's what makes a difference. So here it is a formal proof of that. So suppose consider a CRD set which has a add and remove operation. So suppose if you do a remove and then add element E, then you will get that E belongs to S. And now suppose if you do add and remove E dash and add E concurrently, then you will get E belongs to set S and E dash does not belong to set S. It will be these are all the operations that will be similar to in behavior in sequential and SEC. In both consistency, this kind of operation will be similar. So if you add E and remove E, so here many things can happen. You can either make the last writer wins or something like that, or you can choose based on the IP address of the machines. You can choose any parameter according to your use case. But here they have taken the example that suppose add wins, right? Always. So if you do concurrently add and remove, then it will show that E belongs to S. So if it is the case, then suppose there are three replicas, right? So one replica does add E and remove E dash, and the other replica concurrently does that add E dash and remove E. So now the third replica P2 merges the state from P0 and P1. So here we have for CRDT, we have considered the case that add will win. So regardless of of the remove state, we will get the E belongs to S and E dash belongs to S. So now this type of situation will never arrive in sequential consistency, right? So either remove E or remove E dash will be in the last, right? So because they are done here this way, so one of those will be in the last. So one of the elements will be removed. So there exists a SEC object which is not a sequentially consistent, because this type of operation is does not exist in sequential consistency. So also, so now there also exists a sequential consistent object which is not an SEC. So if we prove this both statement, then we can prove that although there is some intersection between the sequential consistency and SEC, but there exist some elements that which are not intersect, and they are which are not in the intersection, and also the one of them is not a superset of each other. So there is so they are not directly comparable. So mostly for this, so suppose if no crash occurs, then mostly sequential consistent object will mostly almost behave similar to SEC, right? So, but suppose, but sequential consistency requires a consensus. So if there are n minus one crash occurs, then SEC will not work. And sequential consistency will not work. But yes, so SEC will work. So this proves that there exist some elements that are not in both of those. So they are incomparable. So mostly, yeah, this is an example of the increase only counter. So suppose these are three replicas all connected to each other, and these are all the states of other replicas. So now suppose you do add 2 and add 3 in the second replica. So now um, after writing the value of own state and propagating those state to other replicas, what we will get is 2 comma 3 comma 0, 2 comma 3 comma 0. So suppose if someone asks the value, then it will add the all the values in your state and return those. So this is a simple counter increase counter using CRDT. So this is another add only set. So add only set that uh, so mostly they are all partially ordered using the subset. So if you have ordered sets where you can only add and order them using the subset, then they will form a semi-lattice. So mostly update operation will do s dot add of e, then it will do the union of with that element. And so what you can do is that have this like the increase counter, you can have the states everywhere, and um, at every replica you can just perform the union and send it to other replicas which will merge those. And because this will form a semi-lattice, it will be it will perform like a CRDT. So if you now want to add remove set, then you so it is mostly called tombstone set. So you keep two sets, right? So one add state, add set and remove set. So um, so here also you keep the functioning of like the add set or with remove set. But when someone asks to the replica that what is the current status of the set, then what you do is give the difference between the set A and the set R. R is the remove set and A is the add set. So, but yeah, here there will be some constraints that client is allowed to remove only an element that is currently in A. So, and also every element should be unique and should be added only once. Now, this is the third example. So here they are doing currently having a complex example of graph. So suppose we want to create a graph-based crawler for web search engine, then how it might work using CRDT. So, so here is the general working of the crawler, right? So crawler will find a new page and executes the add vertex, right? So for every page, it will compare. So every page it downloads, it will compare that if there is any addition or removal of links in that page. So if there is some change, then it will have to remove those um, links from the database, right? So it will execute add arc. So arc is an edge. So it will add edge and remove edge based on the uh, current version of that URL. So also add edge must work even if the tail is not discarded. So suppose if there is some new link that is referenced in the web page, then although that web page is not discovered, you add edge must work. And also while the tail of that vertex tail of that edge is not discovered, it will not so lookup will fail. So lookup for that vertex should fail because currently we have not discovered it. And so here, so graph can be large, right? So instead of using state-based approach, here they are going to design using, they have designed using op-based approach. So these are mostly alternatives. So suppose a directed graph, which is a pair of sets, vertex and edges. So and edges are the subsets of V cross V. So basically, it is a subset from all possible edges are the subset from all possible edges. So here the invariant for prepare update should be that both head and tail of arc must exist. So if you are updating some arc, then yes, obviously both head and tail should exist. And a vertex can only be removed if it supports no arc. So because concurrently it will provide some problem. And also the system must ensure that the concurrent add arc and remove vertex, so concurrent adding the edge between v dash and v double dash and removing vertex v dash should not violate any invariant, right? So mostly for this, they have considered alternative design. So suppose giving precedence to remove vertex. So so we remove all the vertex and related edges to that vertex, and we can also give precedence to add arc v dash v double dash. So if the vertex was removed previously on that replica, then we will recreate the v dash vertex and add the edge. And also what we can do is remove the vertex v dash, delay the remove vertex operation until all the concurrent operations have executed. But this will require synchronization, because when you will finally know that all add arc operations have been executed or not. So this is not more of CRDT approach of having a synchronization. So here mostly they are going forward with the first approach, that giving the precedent to the remove vertex. So now how the graph will work. So what we'll do is we will keep the two sets, one for vertices and one for arcs, and then how the add vertex operation will work. So prepare update will create a unique identifier for that particular vertex, and effect update will add the pair of the vertex and the unique identifier to the set of vertices. So if the same vertex are added twice, they will be distinguished by the unique identifier, and when you do the lookup, it will mask the duplicates. And also remove vertex, it will compute the set of remove pairs that contains the V. So R is the remove set, and remove that set R from the set of all vertices. So it will mostly remove the vertex V from all those from the sets of all replicas. And also, if the same vertex is removed and add concurrently, then add vertex will win. And it is same for the edge. So, so to remove a vertex, the source replica will check that the vertex is observed. So if it is discovered, and also that it is not the head of any existing arc. And then conversely, for the arc, to add an arc, its head node must exist. But yeah, there is no existence of tail, which we talked earlier. And so yeah, the lookup method will mask the existence as we talked earlier. And so mostly as also concurrent updates may remove a vertex that is the head of an arc, but the lookup method, I guess, will mask such arc. Yeah, so that's it. Thank you. Any questions?